Hi. Our topic for today is equivalence relations. And there isn't much here. This is the natural continuation of the section 6.2. So definition. A relation R is an equivalence relation. If and only if it is reflexive, symmetric, and transitive. I was a little bit careless here. What kind of relation? A binary relation R is an equivalence relation if it's at the same time reflexive, symmetric, and transitive. And these are three properties that we discussed in our previous section. Now, let's see, we want to see here what is so special about these relations that are heavily used in mathematics and basically in other disciplines as well. So, so here's one very typical, actually canonical example how we can make an equivalence relation. Example. Example 61. What would that be? Let P equals A1, A2, A3. And let me make it just a little simpler than in my notes. In my notes I did generally with N. Here I'll go just A3 and A4. Just you get the same story basically. And let us define an equivalence, a relation among the elements of, so let A be A1 union A2 union A3 union A4. But let P be, I didn't finish the sentence, be a partition of a set A. So that means what? You remember what does it mean to be partition? That means that A is equal to the union of these four, and also that AI intersection AJ is empty for I different from J. Generally, what is this? A good metaphor for this is that A is a country, and then these are four states. So just country A was actually split into four states. Here they are, A1, A2, A3, and A4, and each state has tons of individuals. So these are elements of A1, A2, and 3, A4, and then we have the following. For every X and Y and A, we'll say that X tilde PY. Tilde is a Greek letter very often used for equivalence relations, and then index P means it's designed using partition P. That should be proper then. Script P. If and only if there exists I less than or equal 4 such that XY belong to AI. Here's a definition. In three words, that would be they are related if and only if they live in the same state. So it says here, there exists one of the four states so that X and Y live in that state. So they live in the same state. My question is this an equivalence relation? Is delta P an equivalence relation? Now let's argue this carefully. Number one, is it true? So let X be arbitrary element of A. Is X related with itself? Yes or no? Generally, it's fairly simple, but there is a non-trivial start. What is it? Because if X belongs to A, why does X belong to one of the states? Because of this. If they are partition, if X belongs to A, there exists I less than or equal 4 such that x belongs to AI. But then what? I can say then for that I, there's only one, but we don't care even, we don't need that at this point. For that I, x belongs to AI, and we repeat, x belongs to AI, which implies that x is relative to itself. So every person is a state fellow with himself or herself. For second one, what if x tilde py? Can we conclude that y tilde px? Yes, why? Because here it is, a little exercise in proving. If x tilde py, that means that there exists some I, so let there exists I less than or equal to 4, such that both x and y, or let me be a little more careful with this writing analysis here. I can prove that x belongs to AI and y belongs to AI. That's what this column actually means, a little less formal writing. And then what? From here, there exists I less than or equal to 4, such that because of commutativity, that y belongs to AI and x belongs to AI. This is just commutative property of conjunction, which implies that what? Y tilde px. So that means if you and me are fellow fellows from the same state, then the other way around, me and you are also fellows from the same state. And a little more work maybe for the third one. So I'll just write a little less formally, assume that x py and y pz. Why is that x pz implies for the following? There is a little trick here. So x belongs to py, that means that what? X belongs to AI and y belongs to AI for some I less than or equal to 4. The second one, here is a little tricky detail, you have to be careful about it. Y belongs AJ and Z belongs to AJ for some J less than or equal to 4. Why did I use different letter? Because nobody says that their witness between 1 and 4 must be the same. But now comes the crucial detail. I think this needs red. What? Now look at this. J. This was J. For now. Then look at this. Y belongs to AJ, Y belongs to AI. And then what? From here, since they share the same element, and this is a partition, and partition says each two different ones are disjoint. Where's that? Here it is. If I is different from J, then AI intersection AJ is empty. I can do contraposition and get what? If AI intersection AJ is not empty, then I must be equal to J. So since it's not empty, it's because of Y belongs. Y belongs to AI intersection AJ. So AI intersection AJ is not empty, so I must be equal to J. And now what? So now we know that X belongs to AI and Z belongs to AI, because now that J is I, which implies that X is related. So it's really equivalence relation. So remember, that's one of the most typical constructions in mathematics. Whenever we have partition, then partition naturally builds an equivalence relation, and that's a relation between the elements that are in the same state in that partition. And then what? Actually, there is the converse of this. This is really theorem is also true. So here in this example, we are showing that every partition brings us an equivalence relation. And now we'll see the other way around, that every equivalence relation actually builds a partition. When we show that, and that's the main line of this section, we'll actually say the following. Having a partition and having an equivalence relation are basically the same thing in different language. They are just two faces of the same thing. But let's develop that other direction. So definition. So now we will start with equivalence relation and build a partition. Here we started with partition and build an equivalence relation. So here it is, definition 631. It says the following: let A be a set and tilde an equivalence relation. Then for an element let A be arbitrary element of A. So A is the set, and with equivalence relation, and we pick an element little a, any element. Then here is what we define. We define the equivalence class of A. And then maybe I should put here index tilde to say that that's defined using tilde, but just for simplicity of notation, I will assume that that's obvious from the context. Sometimes people also write A/tilde. This would be much better notation, but it's complicated. So what would that be? A set of all B's from A such that the B is equivalent with A. So generally, what is that? So if I have here the drawing, that would be, you look all the elements that are B related to A, the way it is defined, that are sending the arrow to A. So here is one such B, here is the other such B, and so on. All these B's, that's called A class of A. Okay? That's the definition. I didn't finish this circle because I wasn't sure if I should include A or not. So let's play with it and then we will see what will happen. So here it is. Generally, instead of formulating theorem like we did in the notes, we'll go more informally and just kind of investigate what's happening and then make a conclusion at the end. So what are the things that we wanted to notice? First, so fact one, and then we'll summarize them into theorem, which is another nice way to kind of gradually get into a theorem. So fact one, A belongs to its own class. So when I prove this, I can actually finish here and say, yes, A is in its own class. So A is here naming the class. Is it inside? Maybe yes, maybe no. Yes, so why? Because what? A is related to itself because of reflexiveness. So generally, if you look at this, that means if I think of A playing the role of B, so that means A belongs to the set of B that are related to A, so A belongs to its class. What second fact? So generally, no. I can get more from this fact one. Or actually, why don't I say that that's fact two? That when I take a union of all the class, did I say that this is called equivalence class of A? Equivalence class of A. If I take all the equivalence classes, when A changes now, if I move A, that will give me the whole set A. Why is that? Because each element of A is included, because each element belongs to its own class, so obviously this is true. Fact number 3. Is what? That actually, if two elements have a different class, then those two classes are disjoint. I will prove it in a moment, but let's see what is that telling us actually. That when I look at all these classes, that means that what, together with this fact, set of classes, so classes of A, when A belongs to A, constitute a partition. That's the third fact. Because it says that, so I will never have overlap of two of these classes. They are either the same class or completely disjoint. There's never an overlap. Again, I didn't prove this yet, but let me play with it using our knowledge of logic. So if I think of this as P implies Q, I can write it also not P or Q. So that means for every two classes, either they are equal or they are disjoint. That might be a nicer way to say it. Or, as I said, these are three different ways to say the same thing, and now we exercise our knowledge of logic and we see why we studied in the beginning. The way I will prove it is actually, I will prove the contraposition. So I will prove what? If A intersection B is non-empty, then A must be Q. That's one. All three are equivalent, and I'll prove the last one. And how do I prove it? Assume that intersection of two classes, let me erase there so they don't distract us, is non-empty. What does it mean? There exists some C that belongs to A and C belongs to B. What does that mean? That means that C is tilde A and C is tilde B. But then what? If C is tilde A, I can say C tilde B and, no, sorry. I'll keep this one first. A tilde C because of the symmetry, and C tilde B. Now because of transitivity, so what did I do here? I use symmetry. And then A tilde C, C tilde B, I close the triangle. A tilde B is because of transitivity. So I proved that A and B are equivalent, but I'm still not done. Why would that imply that class of A is the same as class of B? So I need still to work on it. So these are sets. So how do I prove that two sets are equal? I show that they have the same element. So I say, all right, how do I prove that? So let U belongs to class of A. Then I need to show that it belongs to class of B, and the other way around, although the other way around goes the same way. So that means that what? U tilde A, by definition of a class. But now we already established that A tilde B, so U tilde A and A tilde B implies that U tilde B, which means that U belongs to B class. And then I should show the other way around. If U belongs, let me show you why not. U belongs to B class. What does that imply? Implies that U tilde B. Then I have A tilde B, so I also have B tilde A. So I get U tilde A, which means U belongs to A class. Here it is. Whenever it belongs to class of A, it belongs to the discal set class of B. Whenever to class of B to class of A, they are equal, and we got this. And that's, now we have a theorem. So we establish, together with the first example and these three facts, we actually established full correspondence between the equivalence relations and partitions. And let me record the theorem on the board the same way. Now it looks much more abstract, but I hope that by now it's all quite more obvious. So that theorem says theorem 631. If tilde an equivalent relation on A, then the equivalence classes of tilde form a partition of A. Furthermore, if we call this partition P, then delta P equals delta. Let me explain the meaning of this, because you start with the delta, with tilde, which is equivalence class. Then when you look at the class of set of equivalence classes, by the way, that's very often called A/tilde. Set of equivalence classes is a partition. And then what? If we call this partition, just for simplicity of notation, if we call it P, and then like in example 1, from that P, we build a delta P, like being in the same state, that delta P is the same as this. Tilde P, sorry, is the same as that tilde from the beginning. And that's quite obvious, and so I'm not going to write the proof on the board. It's just obvious by definitions of both of them. All right, let's see. One more example, and that example is crucial for our section 6.4. That's what we'll do in section 6.4. So that is just to continue the example. If you remember on Z in the last section, we defined congruence relation modulus 6. So A is congruent with B modulus 6 if and only if 6 divides B minus A. So what happens here is the following. If you look at all Z's, then what? One class, let's say class of 0, who's there? Numbers that differ from 0 by a multiple of 6. Who's there? Negative 6, negative 12, 6, 12, 18, and so on. They make one, so we can say the following. All this set, everybody here, this is actually class of 0. Of course, 6 can complain and say, oh, that's my class as well. True, you can call each class, each state according to any representative you want. Like, you don't have to call California according to its governor, like Governor Brown's state. You can call it our state, Chica's state. So each of us is kind of in the same way representative of our state. So what else? There is other state where 1 is, and that's not the same state because they don't differ by a multiple of 6. But who's there? 7, 13, negative 5, negative 11, and so on. What's this? This is state of 1. Why am I calling it 1? 1 is kind of most typical representative. And we'll talk about it more in the next section. Then there is a section of 2. Who's there? 2, 8, 14, negative 4, negative 10, and so on. Here is state of 3. Who's there? 3, 9, 15, minus 3, minus 9. State 4. State of 4. Who's there? 4, 10, 16, negative 2, negative 8, and so on. And I ran out of space for a state. There's one more state, state of 5. Let me just squeeze it in here. So who's there? 5, 11, negative 1. So who's this? This is state of 5. So generally what? The whole infinite set of integers, according to this property, with respect to 6, is divided into 6 typical states. And then basically everybody from the same state has similar behavior, but that's what we'll see in the next section.